Welcome to another video, and today I'm going to discuss autocorrelated regression models, which is a quite important and an essential chapter in understanding the later chapters in time series regression models. So basically I can say that we're gonna jump into the real stuff from here on. Okay, let me just check if the record is going well. All right. Besides that, I just need to check if the sound is good enough. Yeah, it's okay. So autocorrelated regression models. These regression models are used if the disturbance terms are not independent across time. They are not IID. So the specification in a autocorrelated regression model from previous is to look back into previous chapter, previously in chapter 5 when we are talking about linear regression models. A linear model look like this: yt equals beta naught plus beta 1 xt plus ut, residual whether ut was IID with n zero mean and sigma square variance, and the joint probability density function was function of y's y1 to yt conditional upon x1 to xt. Now because we are talking about y1 to yt because y and x both are vectors up until and these both of the information and time series information, so they're progressing over time. That's why y1 to yt x1 to xt. You see, it's important to understand how you represent your recursive model, because in autocorrelated regression models we are mostly going to use a recursion function, so that the recursion function such as RxRR will construct recursive time series models. So the joint probability density function is yt conditional on xt for all parameters. Theta equals beta naught beta sigma square. Let's relax this model of the residual being independent by augmenting the model to include an equation for ut. So ut will not be an independent anymore, the residual will not be independent and identical anymore. So we are going to include an equation for yt, which is a function of information at time t minus 1. So current residual value ut will depend on previous value of residual ut minus 1. Is a function that is also a function of information. So that is what it's meant by a function of information at time t minus 1. So let's look at a ER1 model. A ER1 model looks like this, where the residual ut equals rho1. Rho1 is the correlation coefficient rho1 ut minus 1. So ut depends on ut minus 1, where the coefficient is rho1 plus vt. ARP model is vt is residual from ut. ARP is ut equals rho1 ut minus 1. So this is AR1 model and autoregressive 1 model. Autoregressive p model on the other hand will go up to p ut minus 1, p rho 2 ut minus 2 up until rho p ut minus p, where the rows are the correlation functions, and vt. Moving average 1 MA1 model looks like ut equals vt. So you see, now moving average model will come after ut is residual vt. So moving average is vt plus s1. Oh no, this is not s1, this is delta gamma 1 vt minus 1 gamma 1. So now in moving average vt and the previous value of vt will come up. Gamma 1 vt minus 1. Moving average p model is ut equals vt plus gamma 1 vt minus 1 gamma 1 vt minus 2 up until MAQ model up until Vt minus q. So Vt is in between, you see. So the previous previous model will generate up until Vt, and then moving average will move from Vt forward. Arma PQ model is combining AR and MA model, where the UT is I equals 1 to I equals 1 to P rho I UT minus Y plus Vt, which locates in between, plus I equals 1 to Q delta gamma I Vt minus I is the moving average portion. So Vt itself is a Ut, whether Ut is not independent anymore. Vt is independent and identically distributed with zero mean and sigma square variance. So Vt is a shock at time t, which has an immediate effect on Yt and continue to have effects at time t plus 1, t plus 2, etc. That is what is meant by this Arma model. So it suggests conditional mean in equation beta naught plus beta 1 xt underestimate Vt for some time and overestimate for other periods. So you see, if this is the equation we're talking about, and when Ut has a Arma structure, which means it underestimates the shock for some time, which is this part, and then it overestimates the shock forward, so this part. So example, let's start with an example. A regression model with autocorrelations. So a scatter plot of simulated data for t equals 200 is obtained from Yt equals beta naught plus beta 1 xt plus Ut, whether Ut is autocorrelation function, which is an AR1 function, autoregressive function, rho 1 Ut minus 1 plus Vt. Vt is IID within zero mean and sigma square variance. Theta naught is given, which is beta naught equals 2, beta 1 equals 1, rho 1 equals 0.95, sigma square variance is equal to 9, so that means sigma is equal to 3. Exogenous variable xt equals 0.5 t plus et, where et is also IID with zero mean and 1 standard deviation. Plotting conditional mean beta naught plus beta 1 xt shows conditional mean consistently underestimates Yt for some period and overestimates for other period. A less pronounced similar pattern can be written as this: Yt equals beta naught plus beta 1 xt plus Ut, where Ut is Vt plus gamma 1 Vt minus 1. Vt is IID and zero mean sigma square variance. 60 is theta naught, beta naught is equal to 2, beta 1 is equal to 1, gamma 1 is equal to 0.95, sigma square is equal to 9. Okay, that's great. Alright, so now coming to number 3. From chapter 1, a joint probability density function of y1 up until yt dependent variables, where function of y1 to yt conditional upon x1 to xt for all theta parameters is represented with f function of ys minus 1 to y1. So ys is a predicted model, ys minus 1 is the prediction just before ys, and that comes back to current period y1. So this is a backward propagation conditional upon xs minus 1 up until x1 for all theta parameters. This is marginal. This portion of the joint probability density function is called a marginal distribution. This is called joint probability density function because marginal distribution will add up with conditional distribution. Now conditional distribution is moving yt, function of yt is conditional upon, you see here, y is conditional upon xs and yt is conditional upon its own lag up until and xt, yt is conditional upon its own lag and the lags of x for all theta parameters. So this is conditional distribution, and hence the parameter theta unknown, which contains our unknown parameters, are beta naught, beta 1, then all the rows, because the row coefficients of autoregressive models are unknown to us, as well as the moving average models. All the rows are unknown, as well as all the deltas. I'm sorry, I was saying as gamma is not delta. I'm always messing up with Greek letters. So all the deltas are unknown to us. So the moving average coefficients are unknown to us, and also the variance. Now you see, that is the beauty of time series regression models. Now we are not dealing with beta naught, beta 1 sigma square anymore. It's not that linear and not that easy anymore. Now we have to estimate all the coefficients of rows and deltas, autoregression coefficients and moving average coefficients, which will change the complete structure of our coding. So S is maximum value of P and Q. Now exact maximum likelihood estimator is when both terms are used, marginal distribution and conditional distribution. Conditional maximum likelihood estimator is when just the second term is used. So the whole thing is exact and only the second term is conditional maximum likelihood estimator. S, we get S by maximizing the row P and Q, which P is up until what the maximum recursion for autoregressive models. So the maximum time AR will go on. Then Q is the maximum lags for moving average. So basically the maximum lags from autoregression and maximum lags from moving average is S, which is maximizing this. Now exact maximum likelihood, the log likelihood function of that joint probability density function is now 1 by t mean log of ys till y1 conditional upon xs till x1 for all parameters, plus mean of t, which starts from s plus 1, not s, not exact. It's very important to remember the first row. Things will not start from the first row. The first row, in most cases, we have to trim or remove. So s plus 1 to up until t, and because we need to allow room for recursion to happen. So log likelihood of yt conditional upon its lag as well as xt and its lags for all parameters. So conditional distribution function. The log likelihood function is normally nonlinear. Now you see, is very important, the nonlinear regressions will come into use from here on. The log likelihood function is normally nonlinear in unknown parameter theta and must be maximized using one of the algorithms in chapter 3, by which we talk about Gauss-Newton or Newton-Raphson or BHHH, any of the algorithms we're gonna use. Basically, we're gonna have to kind of like what we did with nonlinear regression, exactly the same way we have to define a function locally, and then we have to maximize to estimate the parameters. So example 7.2, an autoregressive one model where yt equals beta naught plus beta 1 xt plus ut, but ut is not IID here, rather ut depends on row 1 ut minus 1 is lag plus vt, where vt is IID within 0 mean and sigma square variance. The parameter is beta naught beta 1 row 1 correlation coefficient sigma square. The distribution of vt is exponential here in this case, so vt is 1 by root over twice pi sigma square exponential of minus vt square by 2 sigma square. You see, we had u squared by 2 sigma square, now we are gonna have v square by 2 sigma square. The conditional portion, the conditional distribution of ut is when the function of ut, the distribution of ut is conditional upon its lag for all parameters. and going through using the change of variable technique. We are going to initiate that, or FVT is equal to dd of ut vt when we are expressing ut in terms of vt, which is simply well, 1 by root over twice pi sigma square exponential of, instead of vt we put ut minus rho 1 ut minus 1, this portion square divided by 2 sigma square. Now dvt of dut equals 1. Consequently, conditional distribution, because dd of vt by ut, this part is 1, so nothing is coming from here. Function of vt is this, actually simply checking in ut minus 1 ut minus 1 whole square, just like before. Remember, v is the residual here. Consequently, conditional distribution function, on the other hand, yt conditional upon yt minus 1 up until xt for all parameters is fut dut by dyt. Dut by dyt is 1. The differentiation is 1 here. So now we have the whole equation, which was yt minus beta naught minus beta 1 xt minus what, u1. Instead of u1 we can write rho 1 yt minus 1 minus beta naught minus beta 1 xt, because u1 is rho 1 ut minus 1, right, plus vt. That's all, right? So this is ut minus 1. So everything will take lags of everything that goes through time, like yt varies over time, so lags, but beta naught is constant over time, so there is no lag. Beta 1, these are the coefficients which do not change. Which changes is yt and xt, so xt minus 1 whole square. To derive the marginal distribution, this is the conditional distribution function. Now, to derive the marginal distribution of ut, use the result for autoregressive 1 model with ut rho 1 ut minus 1 plus vt, where vt is 0 mean and sigma square variance. The marginal distribution when is 0 mean is equal to not only sigma square variance, but sigma square divided by 1 minus rho square variance. So the marginal distribution function is 1 by root over twice by sigma square divided by 1 minus rho 1 square, which coming from here, rest remains same, ut minus 0 whole square, because simply ut square divided by 2 sigma square as before, but sigma square is not alone because the variance is sigma square by 1 minus rho 1 square, so it will come up. So ut square divided by this one, this portion. Very simple. Now the distribution of yt at time equals t equals 1 is, now we are gonna go with change of variable technique, y1 x1 for y1 conditional upon x1 for all parameters is equal to function of, now we are gonna change y1 to I think u1. So u1, function of u1 multiplied to dd y1 of u1, whether we're gonna put function of u1 is simply, well, 1 by rho 1 square exponential of yt. Instead of ut we put the value of ut, which is yt minus beta 1 x square whole square divided by 2 sigma square into 1 minus rho square. So that is it, you know. And dui, this one dd of yi y1 into u1 is 1, so this one is 1, just like in everything else that remains 1. The next element remains 1 after the exponential element. It's very simple. So this was the conditional distribution previously, this is the marginal distribution. So the joint probability density function at AR1 autoregressive model is the function of the joint probability density function the joint probability density function is equal to fy1 x1 for all parameters, and t is equal to 2 2t. See, remember, first row is not used. Yt is conditional upon lags of yt, xt, and lags of xt for all parameters theta. And the log likelihood function of this is, now first we rewrite whatever we have put here, and 1 by log twice by 1 by log sigma square, half log sigma square, then 1 by t log of 1 minus rho 1 square, because sigma square divided by 1 minus rho 1 square. So, well, because inside the bracket we have sigma square minus 1 minus rho 1 square, when we take the bracket out, we multiply things with minus half, so it remains plus half log 1 minus 1 square 1 minus 2t. First thing is first, 1 minus 2t is equal to, after that what we have is this portion. First we're gonna put this one, then we're gonna, because we're talking about the joint distribution, yt minus beta naught, this is the whole thing coming from conditional, then this is coming from marginal distribution, the whole part. So this is quite a big, adding together the marginal and the conditional, adding together the marginal and the conditional, adding together, we have a big log likelihood function. Log likelihood function is a, so it shows that the log likelihood function is a nonlinear function of the parameters. So first we have just talked about log likelihood function that combines conditional distribution and marginal distribution to give us joint probability density function. Is important. This type of log likelihood function are used for Arma models when you have the autoregressive parameter which leads up to Vt and the moving average parameter which follows on from Vt. Conditional maximum likelihood. So example 7.2 deals with a regression model with an AR1 disturbance term. Estimation of a regression model with the Arma PQ disturbance term is more difficult. However, since it requires deriving the marginal distribution of f function of y's, where s is the maximum value of the lags p and q, one solution is to ignore this term, in which case the log likelihood function in number 4 is taken with respect in number 4. So the log likelihood function, the exact, we're talking about the exact maximum likelihood function. So what we are saying here is that because it requires deriving the marginal distribution as well as conditional distribution, one solution is to ignore this term, in which case the log likelihood function in 4 is taken with respect to an average of this log likelihood corresponding to the conditional distribution from s plus 1 onwards. So one solution, because it's difficult to have a joint distribution, so we can ignore the marginal distribution part, the first part, in which case the log likelihood function is taken with respect to an average of this log likelihood mean corresponding to conditional distribution. So if we are taking conditional distribution portion from s plus 1 onwards, so it will happen up until t minus s. S is removed because you see s plus 1 onwards, which reaches up until t. So t minus s, theta is equal to s plus 1 onwards. That is what is mentioned here, s plus 1 onwards. The likelihood function, we are trying to well, make it much easier compared to our joint probability density function. The log likelihood function of yt is conditional upon the lags of y, x, and the lags of x for all parameters. As the likelihood now estimates by treating the first S observations as fixed, estimators based on maximizing this likelihood are referred to as conditional maximum likelihood estimator. So basically we are just focusing on conditional distribution, and estimators using conditional likelihood function is conditional maximum likelihood estimator, because this depends on maximizing the likelihood based on conditional distribution. Asymptotically, the contribution of log of the conditional distribution function vanishes. So the asymptotically this contribution will vanish as t tends to infinity. Hence the exact maximum likelihood estimator, which is both the parts marginal and conditional added together, will converge to conditional maximum likelihood estimator. Wow. So when we take an asymptotic distribution, this is asymptotic, which means the contributions from the marginal conditional distribution will vanish, and so whatever contribution we receive, if we took the full form, becomes equivalent to only if we take the conditional distribution form. When we fix the first S observations and taking the distribution from S plus 1 onwards, that is the only condition. So an AR2 regression model, in case of an AR2 regression model, we have the equation yt equals beta naught plus beta next plus ut, where the residual ut, because it's AR2, we have to take two lags, because p equals 2 here. So as p equals 2, rho equals 2 here, I'm sorry, so rho equals 2, ut is equal to rho 1 ut minus 1 plus rho t ut minus 2 plus vt. Now, and the parameters are beta naught plus beta 1 plus rho 1 and sigma square, given some values of theta naught, given some initial values, we have rho 1. The conditional log likelihood function is by computing first ut. So the residual yt minus beta naught minus beta 1 xt, we all know that, then vt, which is the residual of ut. Vt is id, ut is not. Ut minus 1 ut minus 1 minus rho 2 ut minus 2, but the parameters are replaced by theta naught. Okay, so obviously initial par, which will replace, if you can remember how it is done in R, par is going to be replaced with the new estimated parameters. The conditional log likelihood function is computed as 1 by log twice pi 1 by log sigma square minus vt square divided by 2 sigma square. So instead of ut square, we're talking about vt square divided by 2 sigma square multiplied to t minus s, right? So t minus 2, and t equals s plus 1 to t, right? So if s is equal to 2, why s is equal to 2? Because there are two rows, row 1 and row 2, because it's an AR2 model. So s equals 2 onwards is fixed. So t minus s, instead of t minus s, we write t minus 2. And because t equals s plus 1 to t, so t becomes 3 to t for vt square. So basically first 2 will be trimmed. First 2 value will be trimmed. In evaluating the conditional log likelihood, it is necessary to choose starting values of the first q values of vt. So it is essential that we choose starting values of the first q values of vt. A common choice is basically v1 equals v2 equals v3 up until vq equals 0. Very good. That means t equals 1 and t equals 2. That means v1 equal and v2 will become 0, and from v3 because t3 to t we are estimating from v3, there will be values that will be estimated, but the first two will be 0. Very good, very clever. Example 7.4, an Arma 11. Now we're talking about an Arma 11 model. So you see, when we are talking about an AR1 model, we don't have to make the initial values 0. When we are talking about an AR2 model, row 1 and row 2 initial values, for the initial values of row 1 and row 2, their first two residuals will be 0. Now let's talk about an Arma 11 model. In Arma 11 we have yt, which is beta naught plus beta 1 xt plus ut, and ut is rho 1 ut minus 1 plus vt plus delta 1 vt minus 1, where vt is IID with theta is equal to beta naught beta 1 rho 1 delta 1 sigma square. Given some starting values of theta naught, the conditional log likelihood function hence is first ut ut is equal to beta naught minus beta 1 xt, and vt, which is ut minus 1 minus delta 1 vt minus 1. With vt equals 0, the parameter is replaced by theta naught, because vt is IID, 0 mean and standard deviation variance. So t equals 2 to t. Why vt t equals 2 to t? Because we are talking about Arma 11, where row row equals 1, delta equals 1. So the first vt or first v1 will be 0, and s will be t equals s plus 1. So s is equal to 0, s is equal to 1. So s plus 1 will be 1 plus 1. So t equals start from 2 up until t. Very good. So vt is equal to ut minus 1 ut minus 1 minus delta 1 vt minus 1. With vt equals 0, the parameter is replaced by theta naught. The conditional log likelihood function is same as before. Only exception is 2 sigma square t minus s. Remember, s equals 1, so t minus 1. There is basically no change. Beautiful. Example 7.5, dynamic model of US investment. Quarterly data is taken for March 1975 to September 2010. Well, quarterly percentage change in real investment, quarterly percentage change in real income, quarterly percentage change in real interest rate is expressed as well, d. Ri is the quarterly percentage change in real income in the interest rate is equal to beta naught plus beta 1 quarterly percentage change in real income, beta 2 quarterly percentage change in real interest rate, real income, real interest rate, and real investment, right? So this is quarterly percentage change in real investment, I'm sorry. So quarterly percentage change in real income, quarterly percentage change in real interest rate plus ut. Ut is equal to rho 1 ut minus 1 plus vt, and parameter theta is equal to beta naught beta 1 beta 2 rho 1 sigma square. All this needs to be estimated, unknown parameters, where vt on the other hand is IID. Remember, ut is not IID. We have t is equal to 214 observations. Now ut on the other hand, from the equation we take all the part on the left hand side. So you see dr real income minus beta real investment minus beta naught minus beta 1 real income minus beta 2 real interest rate. That's all, and vt is equal to ut minus rho 1 ut minus 1. No tricks. The log likelihood function in this case now, first two remains as it is, minus half log t square minus half log sigma square minus half 1 plus half 1 by rho 1 square, because sigma square is not sigma square is sigma square divided by 1 minus rho 1 square for vt. Minus u square divided by 2 sigma square is in general case, but in case of vt, u square divided by 2 sigma square divided by 1 minus rho square, because we have autoregressive parameters. As long as we have autoregressive parameters, this is how the log likelihood function will look. while for t is greater than 1, the log likelihood function is t. For t is greater than 1, the log likelihood function is v squared by 2 sigma square. Very simple. So log likelihood function at t equals 1 is the case here when t equals 1, but when t, there is no change in time, there is no, when it's not varying, the log likelihood function is not varying, we're just looking for one log likelihood function, then it is it. But if we look for varying log likelihood function, a vector of the log likelihood functions, then this is how it is estimated. We need to use Vt squared divided by 2 sigma square. All the parameters are statistically significant at 5% level. So alternative estimators. Now we are gonna talk about the algorithms behind these estimators, but we're gonna just drop it from in here and we'll continue from here again later. Thank you. As we have already talked about the dynamic model of US investment, now we're going to move on talking about alternative estimators for Arma models. Well, previously we were talking about log likelihood function, joint of the joint probability density function, bringing in together a combination of the conditional probability density function and marginal distribution function. And then we talked about how we can ignore the marginal distribution function if we are to begin our function by fixing the initial values of S. And so we are to start from S, which is a prediction, up until t. So now we are gonna talk about alternative estimators, meaning that we're gonna talk about Gauss-Newton, Newton-Raphson, and other estimators. MLE estimators of the autocorrelated regression model nests a number of other estimation methods. To begin with, first the Gauss-Newton algorithm. Exact and conditional maximum likelihood estimators of autocorrelated regression in terms of Newton-Raphson can be derived by finding the log likelihood function based on normal distribution. By concentrating out the sigma square, the variance, and basically you concentrate out variance by imposing 1 or not. In the optimization you do not at all include variance calculation. And non-linearities from contribution of marginal distribution is no longer exists. So if we concentrate out the variance, the non-linearities of the marginal distribution will be completely removed. Once Newton-Raphson can be expressed in terms of analytical derivatives, its rest is simply like other previous methods. So first order derivatives of conditional log likelihood function. So we are not talking about exact maximum likelihood estimation, we are talking about only the conditional portion of the maximum likelihood estimation. So the first order derivatives of log likelihood function of an AR1 model, where with respect to the parameter where we have beta naught, beta 1, rho 1 and sigma squared to be unknown. So dd beta naught of log theta, which is, well, dd beta naught is simply summation of Vt by sigma square, Ut divided by sigma square t minus S. So here we're talking about AR1, so t minus 1 S is fixed, divided by 1 minus rho 1, if you can remember, but we are gonna take the denominator of the denominator up, so Vt 1 minus rho divided by sigma square t minus S. So basically it's very simple. Previously we studied this, that instead of variance sigma square, we use sigma square by 1 minus rho. So this is it. Now because this is first order derivative with respect to beta naught, and you know, in the equations, in the equation we already have well, this is Vt for beta naught with dd beta 1 with respect to beta 1, the log likelihood function. Now with beta 1 we generally have x, so because with beta 1 we generally have x, so and exogenous variable x is related to its lag, so x minus rho xt minus 1 is very simple. So instead of simply 1 minus rho 1, which is the correlation coefficient of autoregressive parameter, lag as well as the parameter lag as well as itself, to itself actually. So starts from t equals 2, because is er1, s equals 1, t equals s plus 1, so t equals 2 up until t, Vt xt minus rho 1 xt minus 1, because it's beta 1. Just remember that this was basically the denominator's denominator which went up, very simple. Then rho 1, when you are taking the derivative, first difference of, well, first order derivative of rho 1, differentiating dd rho 1 log theta with respect to dd rho 1, we have what, v which is IID multiplied to ut minus 1, which is the residual lag divided by sigma square t minus s, very simple. And when we do it, well, when we do it with respect to sigma square, we have minus 1 by 2 sigma square plus v square divided by 2 sigma to the power 4 t minus 1, which is the regular equation. In all this case where v equals well, vt equals yt minus rho 1 yt minus 1 minus beta naught 1 minus rho 1 minus beta 1 x minus rho 1 xt minus 1 sigma square t minus 1. So you see, this is what we did derivatives of. So again, very quickly, when we are taking beta naught, derivative of beta naught, we have rho 1, so 1 minus rho 1 goes up. When we are taking beta 1, we are taking the whole thing xt minus rho 1 xt minus 1, and in the denominator sigma square t minus s as it is, it remains, doesn't go away. When we are taking with respect to rho 1 minus beta naught 1 minus beta 1 rho 1 xt minus 1, when we are taking in respect to rho 1, we have vt and ut minus 1, the lag of ut, vt and the lag of ut. So basically this rho 1 yt minus 1 minus, so simply yt. And when we are taking with respect to sigma square variance, we have vt square, that's all. Now we are going to move into second order derivatives. Now when we again take another derivative of this portion, this portion, now vt vanishes and we have 1 minus rho 1 square sigma square t minus 1 when theta is equal to 2 to t. When we are taking beta 1 square, what happens is that obviously vt vanishes as well, and this one becomes square, 1 minus rho square. You see, second order derivative again as with respect to beta naught. Yeah, so 1 minus rho 1 1 minus rho 1 square, vt vanishes. Here again vt vanishes, x1 minus rho 1 xt minus 1 square sigma square t minus 1. So just a trick, always remember, because we don't never go to third derivative. So first derivative and second derivative, if you can recall, always very easy to do. So the first term vanishes again and the lag remains ut minus 1 square and it is squared. This term vanishes and we are left with 1 by 2 sigma to the power 4 t minus 1 taking this out, then we have sigma to the power 6. So we have basically minus this one minus sigma to the power 6, because sigma square, sigma to the power 4 plus 2, 6. So minus I'm sorry, VT6 divided by sigma to the power 6. Very simple. So sigma square square. That's all. So this is derivative, the second order derivative. Then comes second order cross derivatives. Now we have beta naught, beta 1 both coming into action. So this one was beta naught portion, the denominator remains same, beta naught portion, and beta 1 portion comes in. But if this is second order derivative, so Vt vanishes. Instead of squaring them, now we are just going to multiply the two different terms, beta naught and rho 1. Remember, in rho 1 you have Vt Ut minus 1. Now you have that part as indeed, but with that 1 minus rho 1 from beta naught comes in and that is multiplied with Ut minus 1. Vt Ut minus 1 vanishes. See, the Vt from here vanishes, and we are just remaining with another Vt from rho 1. Then beta naught d sigma square, the numerator becomes to the power 40 minus 1, the denominator, and in numerator you have two terms. For the second derivative of sigma square, you had Vt square, that is one term. So instead of Vt square, now you'll have 1 Vt and 1 minus rho 1 from beta naught. So from sigma square, basically from sigma square you are having 1 Vt, this term vanishes, you have 1 Vt, and 1 minus rho 1. Now beta 1 rho 1, so from beta 1 beta naught was Ut minus 1, so beta 1 is Ut minus 1, beta naught rho 1 was Ut minus 1, 1 minus rho 1. Beta 1 rho 1 is Ut minus 1, same for rho 1, but for beta 1 we have x minus rho 1 xt minus 1, and that portion and that part goes into the second element too, because xt minus 1 is the additional element. The lag of xt, exogenous variable, is the additional element in beta 1, right? Because in the second term, you see what we had here is that Vt Ut minus 1, but in the second term what happens is that for beta naught Vt, for beta 1 Vt xt minus 1, you see, because there's an additional effect of lag in beta 1, which is a coefficient of the exogenous variable or the independent variable, so that portion comes in. This is the coefficient of the constant, so nothing comes in. Beta 1 sigma square, so obviously instead of taking squares, you have the beta 1 portion, x minus rho 1 xt minus 1, and instead of Vt squared, basically Vt and this portion is multiplied, but you have Vt as well, easy. And rho 1 d sigma square, what is coming from here is that rho 1 d sigma square is simply negative. All these, the second order derivatives will be all minus. The first order derivatives were also the second order derivatives are always negative, minus, remember that. So Vt Ut minus 1 for rho 1, for sigma square we have Vt, and for rho 1 we have Ut minus 1 sigma square t minus 1. That's all, simple. So rho 1 d sigma square, what was just rho 1? It was just Ut minus 1 whole square, but instead of that, And what was sigma square? It was just sigma Vt square. But rho 1 sigma 1 is just taking, instead of taking the squares, you just take the stuff from each Vt and Ut minus 1. Very simple. Now setting the dd sigma square of log theta 0 and rearranging the concentrated that we are to concentrate out this variance, which is summation of v square divided by t minus s. In this case s equals 1, so t minus 1, something to concentrate out a sigma square in the out of the log likelihood function. The iteration after concentrating out, the iteration is expressed in the updating scheme. Basically is beta naught, beta 1, rho 1, because sigma square is not there. K minus 1 minus gradient inverse Hessian. The gradient is obtained from 1 1 by sigma square t. You have z1, z2, z3. What is z1? From beta naught, z1 is only 1 minus rho 1. From beta 1, z2 is xt minus rho 1, xt minus 1. You already know it. From rho 1 is ut minus 1. The main elements, right? Just the main elements are coming in that we are left with. And mean of this multiplied to 1 by sigma square. 1 by sigma square residual, which is u square divided by t. Now you see, it's very simple. In this estimation method, what we did first order derivative, we did second order derivative, and we did cross order derivative, from which we assumed the sigma square, the differentiation of sigma square is 0, and because we are concentrating out the estimated variance, and so the updating scheme we introduced, and we told that in the gradient these elements will remain, and following first order condition, using the first order condition results, you have Vt, which is IID, to be 0, and so Vtxt is also 0, which follows from first order condition. And because this is coming from the first order condition is all 0, so Vt indeed is 0, as well as if Vt equals 0, then Vtxt is 0 too, right? And hence the Hessian is again mean, negative sigma inverse sigma square, the gradient portion 1 minus rho, whatever this is the gradient portion. Negative Hessian is the gradient portion that is multiplied to each element 1 minus rho 1, xt minus 1, xt ut minus 1. So this is Hessian. So substituting a into b, we are remained with the ZTVT divided by ZT prime, where Vt is ut minus rho 1, ut minus 1, ut is this, minus rho 1 is the lag of ut, very simple. Zt is 1 minus rho 1, this is Zt, 1 minus rho 1, xt minus so there are z1, z2 and z3. These are z1, z2, z3 multiplied to Vt and Zt transpose. That's the cell. That's it. This is a row vector. This one is multiplied with a row vector, and in the row vector you have z1, z2 and z3, which are the main elements of the second order derivative for beta naught, beta 1 and rho 1. That's all, very simple. So all parameters are evaluated at k minus 1, because k minus 1 is the initial parameter estimation that you are going to use for the updating scheme. Do not forget what the values of z's are, because they are essential, absolutely essential, and this is exactly the same as the nonlinear regression model, where we separately estimate put in the z values in the functions and then we use them. The updating algorithm has two important features. It does not contain variance sigma square, estimated sigma square, as that is cancelled out in calculating the gradient divided by Hessian. Okay, beautiful, because this portion is there in Hessian and that is also in gradient, so you just cross them out. That's all. So in the updating scheme, this is already automatically concentrated out. The variance is automatically concentrated out. It is equivalent to Gauss Newton consisting the regression of Vt on Zt, if you can recall from the nonlinear regression model, because autoregressive models are largely nonlinear in the first stage. So regressing Vt on Zt. A simpler way to motivate Gauss-Newton algorithm in one is to express the model in terms of Vt as dependent variable, just like previously when we expressed the equations in Ut. Now you have an additional element, so you cannot, because Ut is not the residual anymore, so you have to express the equation in Vt. Previous chapter we expressed the equation, we began by expressing the equation with Ut, and now we are going back to what we studied exactly what we studied in the previous chapter. So first Vt equals Ut minus 1, Ut minus 1. Now you know Ut is regression, which is this and the lag of this, and then the derivatives, we know the elements of the derivatives. So beta naught, beta 1, rho 1. This is mistaken, this is beta 1. So 1 minus rho 1, x minus rho 1, xt minus 1, and Ut minus 1. Very simple. See, this is exactly the same as what we did before. Okay, fine. Now move on. Example 7.6, Gauss-Newton estimator of an Arma 1-1 model. Right, so this is an example just to practice. So first express the equation in Vt as we have studied before. An additional term, this is autoregressive part minus this is the obviously moving average part, delta 1 Vt minus 1. So Vt beta naught, then this is autoregressive part minus delta 1 Vt minus 1. So construct derivatives. This is Arma 1-1, so this was the element 1 minus 1 for beta naught minus delta 1 z1 t minus 1. Z1 was this, so delta 1 z1 t minus 1. That's all, very simple, the whole equation again. Then z2 is beta 1, which is this portion, this equation that we already are familiar with. Then delta 1 z2 t minus 1. Z2 t minus 1 is just taking t minus 1 of the whole equation here, right? Exactly the same thing, because this is Vt. So we have to take the lag of the entire equation. When we this is z1t, right? And then z1t minus 1 is the lag of z1t, because this is an updating parameter. When this is a autoregressive equation we're talking about, it's not like before. z2 t minus 1, so it's a recursive estimation. So we have a function called rexerror in MATLAB that automatically do the recursions. Then this is yt minus 1 minus beta naught minus beta 1 xt minus 1 was the parameter of was the element of rho 1. But let's have a look one more time. Ut minus 1 was the element of rho 1, right? So Ut minus 1, this is Ut minus 1, but instead of Ut minus 1 you can write, I mean taking everything on the right hand side, you can write this, and then minus delta 1 z3t minus 1. Then finally delta itself is the fourth parameter, right, which is V. Delta is nothing but V, the lag of Vt minus 1 minus delta 1 z4t minus 1. So very simple. First we, just like before, we expressed the estimate Arma 1-1 in terms of Vt, then we construct the derivatives of Z, and then we regress V on Zt. So we construct the Z matrix, and then we regress V on Zt with all terms evaluated as starting values beta naught, beta 1, rho 1, delta 1. and then we go on estimating the deltas, the changes. So this was the starting value, and then we go on repeat iteration to estimate the deltas until convergence happens. So 1 0, and this is the deltas. So just like the previous chapter, we set a convergence criteria, and this iteration will continue until convergence happens. Beautiful. This is Gauss-Newton. Then another method is zigzag algorithm. The derivation of Gauss-Newton algorithm is based on using the first order condition to simplify the Hessian. So the objective was to simplify the Hessian, isn't it? If you look back, we are left with gradient multiplied to the gradient elements in rows, z element in rows. That is the easiest Hessian we have ever seen compared to before. Another way to proceed for further simplification of Hessian is to use the scoring algorithm. So we know negative Hessian equals information matrix, or OPG, outer product gradient, or J. We need to derive information matrix in this case, and this is the equation. This is the equation where this is the equation where we have first yt equals beta naught beta 1 xt plus ut, and then ut, obviously the value of ut, where vt is iad not ut, and taking the second order derivatives and the cross order derivatives. So now second order derivative beta naught is, we know we are left with 1 minus rho 1. Beta naught square is simply 1 minus rho 1 square. We know beta 1 is x minus rho xt minus 1. So exactly it is squared because we're talking about squared. It's not a cross derivative. Everything else remains same. We know rho 1 is either ut minus 1 or ut square. Well, 1 minus basically ut square itself, u square equals sigma square divided by 1 minus rho 1 square. So sigma square t minus 1, cross it out, and you have 1 divided by 1 minus rho 1 square. Now you can ask that, oh, we had ut minus 1 before, or it should be ut square. Obviously it is ut square because sigma square equals u square. It is the variance. When you square the residual, you have the variance, and the variance crosses off. And so this is obviously up until t minus 1. So you are left with 1 by 1 minus rho 1 square, because time doesn't matter here. In the variance portion, n square, this is again exactly the same as before, 1 by 2 to the power sigma to the power 4 minus v square divided by sigma to the power 6t minus s, and v square is u square, where this is probably what you are left with, because we are talking about expectation on this of v square, and expected value of the residual is 0. So the whole thing is 0, and we are left with this. Makes sense? Doesn't make sense, because it's not that. Basically this is sigma square sigma to the power 6 crosses off, you are left with sigma 4, and then because you're taking expected value, t starts with 2, so it's basically half mean, that's all. So this is coming from here, and this one is basically nothing. This one vanishes, so you have this. And then we are talking about the cross derivative, and when we are talking about the cross derivative, again here we are expressing it in expectations. So some things will vanish when you're taking expectation. That's the benefit of taking expectation. For beta 1 we have the beta 1 element, which is z2. For beta naught we have z1, 1 minus rho 1. Fine. For rho 1 we have rho 1 element, which is just like before, ut minus 1, 1 minus rho 1, and rho 1 beta naught is adds vt to and rho 1 beta 1 with vt adds xt minus 1, because instead of 1 minus, here vt is alone, here vt is not alone, because vt has x with it. This was constant, so this has nothing, this has x, and b naught is z1, beta 1 is z2, which is xt minus rho 1 xt minus 1. Beautiful. Then come beta naught sigma square. Sigma square, for beta naught we have 1 minus rho, which is z1. For sigma square we have vt, the residual IID. For beta 1 we have z2 xt minus 1 xt minus 1, and for sigma square we have vt, same thing, and rho 1 sigma square. So for sigma square we have vt, and for rho 1 we have ut minus 1. Exactly, for rho 1 we always had ut minus 1. So that basically is part of the information matrix.